Hi, I'm Mr. V. Today we're talking illustrative mathematics, Unit 4, right triangle trigonometry, and this is Lesson 6, working with trigonometric ratios. We start this with our Bellwork, which was to find a line that is going to be between each of these. And one way to do this would be to draw a point, maybe right here is one, and another point, maybe this one. If I were to draw a line through these 2 points, we'll see that actually fits our criterion. Yes, it does sort of, maybe it hangs a little close to the lower side, but it's still going to be through all of these points. And how would I find the equation of this line? This is a review from Algebra 1, where we have the y-intercept, which is 0, comma b. Our b value here is going to equal to 3. And our slope, if we make a slope triangle, we have a rise and we have a run. This is a rise of 4, a run of 6, or we could do a rise of 2, a run of 3. This is our slope, which is our change in the y direction versus change in the x direction. So it's going to be 2 over 3. And if we use the y equals mx plus b format for form for the equation of a line, there are other forms we could use, but we'll use this one. Our slope is 2/3, and we'll multiply that times x plus our b value, which is our y-intercept, is 3. This is the slope-intercept form, equation of the line. Next activity that we were supposed to do in this, it says, first of all, the objective. By the end of the day, you would be able to say, I can use sine, cosine, and tangent to find the side lengths of right triangles. So here's a problem. This is one that we did at the very first of class, first part of this unit, when we actually had to find the missing side. When we knew two sides, we could use the Pythagorean theorem. Here we can't. So what are we going to use? This is my technique for doing this. I would like to suggest that you do this when you have a right triangle from this reference angle. So it would be different if I were using it from 40. But from this angle, this is the adjacent side. I would use an A. I'll write it out ADJ here so that you can see it. And this Z, which is what I'm looking for, is the hypotenuse. So if I'm looking for adjacent to hypotenuse, the adjacent to hypotenuse ratio would be adjacent length to the hypotenuse, this one. At 50 degrees, I'm at this point. This ratio, which is a decimal, but it's really a ratio of the adjacent to the hypotenuse, is 0.634. I mean 0.643. And I want to see if this is the same as what I get when, or what value of z would make this work. No, I want to see if this is going to equal to 10. I think is what if this is going to work if this is 10. Does it work if this is 10? I don't know. Let's just calculate it. It's not going to be 10. If I wanted to calculate this, this is equal to the ratio, I'm thinking of another problem, excuse me, of 3 to z. I want to get z by itself. How can we solve a proportion? Any proportion can be solved using the cross product property. Multiply the means by the extremes. So we have 0.643. Z is equal to 3 times 1. And if I divide both sides by 0.643, I get the answer. Now I'm going to let you do that on your own calculator. We could do it right over here on the Desmos scientific calculator. In fact, I could do it right now, just as 643. And when I do that, I'll plug it in here. 3 divided by 0.643, and I get 0.47. So my z value here is equal to 0.47, or it's approximately equal to 0.47, 4.7. Next in line for my Desmos thing here. This problem was one that we started with at the beginning of the unit, didn't know how to approach it, and now we have a strategy for finding the lengths of triangles and acute triangles. The purpose of this lesson is to teach you a method that works for any angle, not just the ones that are in our right triangle table. So if we use, if we read this article, I'm going to read it out loud because it's that important. So the right triangle table is useful, but what if the angle is not a multiple of 10? There must be a way of estimating or calculating. The name in the column of the right triangle, adjacent leg divided by the hypotenuse, that's this one, is what mathematicians call the cosine. And so I can write that in this table. I'll write it up here at the top. C-O-S-I-N-E. And we're going to abbreviate it cos for cosine. The column labeled opposite leg divided by the hypotenuse is the sine. It's this one. And we will abbreviate it S-I-N. That is not sin, that is sine. The ratio for the opposite leg divided by the adjacent leg is called the tangent. It's also what a female geometry student was looking for on the beach. But we were going to abbreviate that T-A-N, tan. And these three names, the tangent, cosine, and sine, represent the trigonometric ratios. So from now on, instead of calling it the adjacent leg divided by the hypotenuse, we will call it the cosine, or we'll call it the sine, or the tangent. These words come from the root of trigon, which means like a pentagon, a hexagon. You know, trigon is a triangle, and metric means to measure. So measuring a triangle is what it really means. Cosine, sine, and tangent work like functions. The input is an angle, the output is a ratio. So if we input 50 degrees, we get an output of a cosine of a ratio. And this ratio can be expressed as a decimal or could be expressed as a side divided by a side. And so in our example, well, first of all, we have, what if we put in to our thing here, sine of 45? What if we do the cosine or the tangent of 45? It equals to 1. Why is that? Let's just look at what we're viewing here. If we have a right isosceles triangle, so this is going to be half a square. This is 45, and this is 45, and this is 90. So if this is x, this would be x, and of course the hypotenuse would also be x times the square root of 2. So from this angle, if this is 45 degrees, this would be the opposite, and this would be the adjacent. If we're looking at the ratio of the tangent, which is the opposite divided by the adjacent, that's going to be x divided by x, and that's just a giant 1. That's all it is. That's what it is, 1. That's why the tangent of 45, the opposite divided by the adjacent, is equal to 1. We can also type in the cosine of 50. So we had this expression, and so we should get 0.643 when you do the cosine of 50. And on some calculators, so not 5, cosine of 50, 0.643 when we round it to 3 decimal places. If you're not getting that, it may be because you're not using degrees, you might be using radians. It would give you a different value if you're using radians from degrees. So this was our big discussion today, and now the rest of this class was spent on doing some practice. First, we filled out this table. In this table, we calculate the value. We put in the values. So we do the cosine of 50, we get 0.643. If we do the sine of 50, so we have sine of 50. That's 0.766. If we do the tangent of 50, so I'll do the tangent of 50, we get 1.192. If I do the cosine, anyway, I can do these other things here. I'm going to do just the cosine of 40 to show you what this looks like. Cosine of 40, 0.766. What? That's the same as it was for the sine of 50. So if I have this triangle, it's a right triangle. This is 40. This is 50. And from 50 degrees, my opposite side would be this one. And my adjacent side would be this one. Wait a minute. The hypotenuse is over here. That's from 50 as my reference angle. If I use 40 degrees, this would be the adjacent and the hypotenuse. Well, the ratio of the adjacent to the hypotenuse is the cosine. The ratio of the opposite to the hypotenuse is the sine. And I have a mnemonic device to help you remember this. This is not scientific. It is only to help you as a memory aid. And that is, when we have the sine, it's the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse. And the tangent is the opposite over the adjacent. And we say, so, ka, toa, or so, ka, toa, SOHCAHTOA. SOHCAHTOA is to help you remember, oh, the sine is the opposite of the adjacent, of the hypotenuse. Ka, well, that's the adjacent of the hypotenuse. And in each one of these problems, I would encourage you to write down here from this angle, from 50 degrees, this is going to be the adjacent leg, this would be the hypotenuse. So the ratio of the adjacent over the hypotenuse is equal to, for 50 degrees, is going to be 0.643, which is equal to 3 over z. And we've solved this problem once here today. So this is the summary. This is things that you should write down in your reference table. There's cosine, sine, and tangent. Cosine, adjacent over hypotenuse. Sine, opposite over hypotenuse, and tangent, opposite over adjacent. So let's look at some problems, some practice problems. From this reference angle, this is the adjacent, this is the hypotenuse. Which trigonometric ratio is it that does the a over h? That would be the cosine. So the cosine of 17 is equal to the adjacent, 10, over the hypotenuse, which is x. To solve this, I'm going to cross multiply. When I do that, I can divide both sides by cosine. So actually, these two items switch places. So I get 10 divided by, and you should try this division just to make sure that you're comfortable with what I just did. If you want to, you can write out the cross multiplication. You can see how this works. So when I type in 10 divided by cosine of 17, I get 10.5 as approximation. So this is approximately 10.5. On the next practice problem we had, this doesn't look very familiar, but 48 plus 42 is 90. So this third angle of the triangle has to equal to 90. You have to sum to 180. You might want to redraw it if you feel more comfortable. That's fine. I'm going to go from this angle. I could go from the 48, but I'm going to go from here. This is my adjacent. This is my hypotenuse. No, that's not right, is it? Maybe I should redraw it. So this is my adjacent. This is my hypotenuse. So I could write, let's see, the adjacent to the hypotenuse. That's not so, it's ka, the adjacent to the hypotenuse. That's why we write this out. So SOHCAHTOA, to help us as a memory aid, remember which trigonometric ratio to use. The cosine of 42 is equal to the adjacent, y, divided by the hypotenuse. So if I multiply both sides by 7, this becomes a 1, and this becomes 7 times cosine of 42. When I multiply that out, 7 cosine of 42, I get 5.2, approximately 5.2. Here I think we're supposed to find all the missing sides. Oh dear. So we have a triangle. We have x is 90 degrees. We have y is 12 degrees. And we have side xz, which would be this one, has a length of 2. From this angle, this would be the opposite, this would be the adjacent, this would be the hypotenuse. I can find the third angle by subtracting it from 90, subtracting 12 from 90, because if I subtract 90 from 180, I get 90. These two angles have to be complementary. So this would be, what is it, 90 minus 12 would be not 88, but 78. Now, to do the rest of this problem, if I look at the opposite over the adjacent, that would be the tangent. The tangent of 12 is equal to 2 divided by a. To go the opposite divided by the hypotenuse, I would say opposite over the hypotenuse, that's so, or sine. The sine of 12 is equal to 2 over h. So I can plug these in the calculator and solve them. I'll let you do that. This one, I could do it with the trigonometric ratios. I could use 60 degrees. But notice, here we have this. This is half of our equilateral triangle. This is one that we remember. It's one of those special right triangles. It's a 30, 60, 90 right triangle. The half an equilateral. The hypotenuse is double the shorter leg. Knowing this will keep you out of trouble. The longer leg is opposite the angle that is 60. It's root 3 times the shorter leg. And isn't that something nifty? This third one, which we're supposed to draw a picture of, we have angle K is 90 degrees. So we'll put K here. And L is 71 degrees. So I'll put L at this point because this looks more, a little bit bigger, 71. And side LM, so M is going to be here, is 20. Well, I can find the other angle here by subtracting 71 from 90. I get 19 degrees. Now I'm going to use this angle as my reference angle. From this one, this is the opposite, the hypotenuse, and the adjacent. So if I set up a ratio of the opposite to the hypotenuse, that is so, our sine, the sine of 71 is equal to opposite over 20. And you can multiply both sides by 20 to find out what O is. To find out the adjacent, I have the cosine. The cosine of 71 is equal to the adjacent divided by 20. Multiply both sides by 20 to find out what A is. One of the things we do is to fill out this table. So if I look at the cosine, sine, and tangent, tell me what you think it's going to be for 90 degrees based on the pattern that you see in here. I'm not going to do this. I'm going to let you do this on your own because I think it's straightforward that you can try it. Here we have two angles. These are from this angle, from 55, this would be the opposite, and this would be the adjacent. Whereas from this angle, as our reference angle, this would be the opposite, and this would be the adjacent. They're kind of just backwards. Notice that these are complementary angles, and this is why in our table it looks like it does. If I look at the ratio of the tangent of 55, that's going to be the opposite divided by the adjacent. That's equal to D over E. If I look at the tangent of 35, this will be flipped. It'll be E over D. Now watch this. Watch this. If I do the cosine of 55, that's the adjacent over the hypotenuse, that would be E over D. I'm sorry, E over N. What am I thinking? E over N. Adjacent over the hypotenuse. I'm going to do the sine of 35. Because for the sine, it's going to be the opposite of this one, divided by the hypotenuse. That's E over N. Oh, wait, that's the same thing. The cosine of the 1 degrees is the sine of the other. These are just switched in our table. Remember that? And for the cooldown, we have to find all the missing sides and angles. So if this is 24, what is 90 minus 24? It'll be 66 degrees. If this is 8, and from this angle of 24 degrees, I'm going to say this is the opposite, and this is the hypotenuse. So if I look at some trigonometric ratios, I can say the tangent of 24. Tangent is the opposite divided by the hypotenuse, which would be O over 8. Multiply both sides by 8 to find out what O is. If I do the opposite over the, or adjacent over the hypotenuse, that would be the cosine of 24. From this as my reference angle, not 66. So I would get the cosine would be the adjacent over the hypotenuse. Here we cross multiply. I get h is equal to 8 over the cosine of 24. Make sure that you know how to do that and where that comes from. do the cross multiplication, and it will show you. Good luck and success.